So today you're going to see simulation diagrams. And this is a very important tool in this class. Well, the class itself is called Systems and Simulation. So the idea now is to convert those differential equations that we use to create transfer functions into simulation diagrams. That will give us a more visual representation of a system. And that will also highlight how internal variables are related to one another. When you use a transfer function, that's a very useful tool in the sense that we can have explicit relation between two variables in the system. But the internal variables, what is happening internally to the system, is gone. We don't have access to that. What I mean by this is, imagine that you're trying to control, let's say, the position of a mass spring damper system using a DC motor. If you want to find the transfer function, you have access, say, between the displacement of the mass and the voltage applied to that motor. We don't have access to the speed of the mass. We don't have access to the current in the motor, to the voltage in the motor, and so on. I only have access to the input and to the output, but nothing in between, which is a problem in the sense that if you want, for example, to develop a system, a controller for that system and ensure that the voltage doesn't exceed a certain threshold, we'll need to probe the voltage somewhere in the simulation to make sure that that requirement is met. And same goes for other variables such as the speed, acceleration, and so on. So the idea in today's lecture is to convert these differential equations that we've been using into a graphical representation that you can explicitly simulate in Simulink in particular. And then we have access to all internal variables in the differential equations, and also highlights how these internal variables are interdependent. And one easy way to see this is later to implement these differential equations into Simulink using this block representation rather than the transfer functions in MATLAB. So the idea for today's lecture is to represent any equations or any control system or any system in general using block diagrams, and also represent transfer functions using block diagrams. Let me give you an example. Here we have the position control system of a spacecraft platform that is governed by the following equations. We have a set of 4 equations, and clearly here we are controlling a position of the spacecraft. So we have a desired position where you want the spacecraft to be. We have its current position, which serve as reference for us to know in which way we should steer the spacecraft. And we have now a set of equations that will describe the process of applying a voltage to a controller, and the controller taking action to change the position of the spacecraft. So this is governed by this set of equations with internal variables. And if you want to simulate this with a transfer function, we would only have one equation. You have to combine all these 4 equations, and you have then the relation between a desired output and the current output. That's it. But now if you are able to simulate this with a block diagram, we have access to all these internal variables that are necessary to make this process work, such as the current and the voltage in the amplifiers, the motor shaft position, and so on, whatever is internal to that system. Another thing that this will help us do later in the next lecture is to do the opposite process. We can go from transfer functions or from differential equations to block diagrams, but we could also do the opposite and go from a block diagram back to a transfer function. All right, that will be the focus of the next lecture. Now, going from equations to block diagrams is relatively straightforward. The opposite is not always true, and the students seem to struggle with that part a little bit, so we'll take it slowly and we'll see how that goes. So what is a block diagram? We have already used Simulink for one of the labs, so we have pretty much we have an idea what I'm talking about. The idea is to now take equations and represent them in the form of a block diagram, in the form of a block element that has an input and an output. So in the block, we have the function, a function of S, that represents the system. And now this system is given an input. We pass that through the transfer function or through whatever equation goes in there. And then we have the output on the other side. Or we can have multiple inputs and multiple outputs for the same system as well. Right? So this, for example, here is the relation between the input voltage and position of a DC motor. What you see inside there is the dynamic model of the DC motor. Now we can apply a voltage, and on the other end, we have the position. But we could, instead of just having this single block diagram, to have a more detailed block diagram that would expose other internal variables as well. And you're going to see that that is indeed possible to do. We'll derive this from scratch later. Using the block diagrams, you see that sometimes we have not necessarily just a straight input to output relation, but it may have the output being fed back into the input to the system. And this is very common in physical systems, in the nature, when you have some sort of a feedback, some sort of way to observe what is happening in the system, and then use that information to create a logic to control that system. It's not necessarily a system that will have one input, pass to a function, and goes to the output. These type of systems, we call them open loop systems, in the sense that we give an input, we pass the input through a process, and then you have the output of the system. If you want to control such a system, we need now to have a good understanding of that process, that a system that we are trying to control, and then create a logic to make that system behave the way we want. For example, let's assume that this process was the speed control of a car, for example. Or the system is the speed control of a car. So the process is the car itself, is how the car will respond to acceleration, for example, or to an angle, throttle angle. If you want to control the speed of the car, we'll need to develop now a controller. This controller needs to create some action. So for that purpose, we have an actuator, anything that I can apply a force or a voltage or whatever input to the system. And then combined, we have a controller that takes actions, that decides what actions needs to be taken, the actuator that takes those actions, and then the actions are given to the process, and then you have an output. So in this case, for example, here, if the process is the car, the actuator could be the throttle angle, or whoever is pressing on the throttle, and the controller is the logic behind that. If I want to increase my speed by 10 meters per second, I have to press on the throttle by this much. That would be the control logic behind it. But you see here that this is an open loop. We are not watching the output of the system. We are trusting our judgment. We know the process well enough such that we can take these decisions based on our understanding of how the car behaves, how the car responds to an input. So open loop control just goes one way. We know how the process works, and then we can devise a logic based on our understanding of that process. But that's not necessarily always the case. We may have other systems where our understanding or our model of the process is imprecise. And in that case, we cannot establish a precise logic to control it because of, let's say, we don't have a model that is accurate enough. We don't know exactly how the system works, and so on. So we can now close the loop and have another element here in the simulation, which is the sensor, is whatever is measuring the output of that system. For example, in the speed of the car, we have a speedometer now giving us the speed of the car. And we take that measurement and you feed it back in the input. What does that do? Well, now we are taking actions not based on the absolute speed of the car, but based on how far we are from the speed we want. Notice that a little circle in the beginning there, the very first element, that's a sum. We are subtracting the current output from the desired output. In other words, we are calculating the speed error for the car. We are this far away from the speed we want. Now to get there, what do we need to do? So this is a different logic. In the first one, we are controlling the absolute speed of the car, assuming that we know how much I have to press on the throttle to change the speed by that amount. Now the idea is a bit different. Instead of targeting a certain speed, our goal is to minimize the error between where we are and where we want to be. All right, so you see the comparison happening at the beginning there. We'll go into these details later, but this was what we call a closed loop control, and you see this in many physical systems. They appear naturally. There is some sort of information about the system behavior that is fed back in the controller, and the controller uses that information in order to control the system properly. So for example, here, back to the car, if we know this is a DC motor, we are controlling the speed of a DC motor, for example, and we know that if by every volt we apply to the DC motor, the speed increases by 0.5 radians per second. So the model itself, G of S, which is the motor, can simply be represented by data value. Of course, we are neglecting all the dynamics, but we know that if we apply this voltage to the motor, the speed on the other side is the voltage times 0.5. And this is a very simplistic model. It doesn't take into account any dynamics. It's just a static model. Now the block there that is empty, that's our controller. Now we need to make a logic that will tell us how much voltage we want to apply. We need to apply to get to the speed we want. Let's say, for example, if you want here, you want the motor to run at 10 radians per second, what voltage needs to be applied to the motor to get 10 on the other side? 20, right? It has to be 20, which means that there is a gain here, which is 1 over 0.5. And that's our control logic. We'll divide the desired output by 0.5. That gives how much voltage we need to get to apply to the motor. And that dictates then the output speed. Now, again, we are assuming here that we have perfect knowledge of what is happening in G of S and how the system behaves, which is not always the case. We are, first of all, linearizing systems that are not linear. We are making assumptions about their behavior. We are making the assumption that they don't change over time. And you're also making the assumption that in the case of the car, there are no external elements acting on the car. But what if you're going uphill or downhill? That's not part of the car model. It's an external disturbance. It's an external force, an external factor acting on the system. And that cannot be captured by G of S, because G of S is just the car itself. So this works so long as we know perfectly how the process works and there is nothing else acting on it. So that's not always the case. And that's where the idea of closing the loop now comes in. Because even now, if our model G of S is not accurate, we are no longer looking at the absolute speed and the output. We are trying to minimize the error between the desired speed and the output speed. Right? So any external elements acting on the system will automatically be accounted for by that feedback loop. And as I said, this feedback loop is available, appears naturally in several different systems. So overall, this is the loop we are going to use to represent some systems, especially when you want to add control to them. We have all these elements. And for example, if you do temperature control in your home, what are we doing actually? We have the house itself is the process. The actuator is the furnace, is how long the furnace is on or off. The controller now is a logic that will turn on the furnace on and off depending on how far you are from your desired temperature. For example, if you are 2 degrees under the temperature you want, we have the desired temperature, let's say at 22 Celsius, and the current temperature at 20. That creates an error of 2 Celsius. So the furnace now knows they have to increase the temperature by 2 Celsius. And that's the control logic that will now decide how long the furnace goes on. Right? What would be the disturbance here? Well, the disturbance is the outside temperature that may change over time and may influence how the house responds to opening or closing the furnace valve at a given time. Right? So this sort of feedback will now appear in several lectures, and not necessarily when we want to add control to a system, but naturally they appear in many physical systems. You'll see the example of a DC motor that has such feedback loop there. So to do all that, we need now to start creating the simulation diagram. So the first thing we need are these building blocks to create these simulation diagrams. Here are 2 of them. The first one is the most elementary one, is the transfer function. One block with a transfer function will have an input and an output. And you know that the output of this system will simply be G of S times X. Of course, X of S and Y of S. And by convention, we use a square to represent the a transfer function with one input and one output. The second element here is what we call a gain, which works like a transfer function, except that what is inside of that element is not a function of S, it's just a constant. And for that matter, we are going to use a triangle to differentiate it from a transfer function. And you can also note here that Y of S is alpha times X of S. Right? Output equals to input times the function inside there. Right? And you can continue. This is the last one we need. We now need a summation and subtraction. And these are the three most common ones we're going to use. We are going to represent that using this circle. Let's call here the output Z. So you see two inputs going in the block and one output. So the first one, when there is no sign, we can assume that that corresponds to a sum. So we can say that a Z equals to X plus Y. In the second diagram, we see that Y has a negative sign. So that would be Z equals to X minus Y. And in the third one, we have the negative sign on X. So Z equals to Y minus X. Right? Okay. Now, one simplification here that we can do later is when you have transfer functions in cascade like this. And let's put here a signal Z. We know that a Z equals to G times X. You know that a Y equals to H times Z. So we may combine G and H into a single block and simply multiply them because they are in line. The signal is in line. And now we can write that Y equals to G of S times H of S times X of S. Does that make sense? Yeah. Okay, and that's all. That's all the elements we need. Relatively simple, and you find every single one of these in Simulink. And you use this for the labs and for the next assignment as well. Okay, so now let's apply all this to a DC motor, and let's see if you can represent the DC motor using a block diagram representation. So the DC motor, if you look at the physics of it, there is going to be two distinct parts there. One is the mechanical and one is the electrical. So as you apply a voltage to the electrical part, that creates a current. The current creates a torque, and the torque starts to rotate the mass, the rotor mass, and the rotor has an inertia and has friction. So there are two distinct components, the electrical and the mechanical part, and there is a link between them. We're going to see. Well, let's now try to model this. So let's start with the electrical circuit characteristics. So the electrical circuit can be represented simply by a LR circuit, but you need to add another component here, because when we turn this on, there's going to be a current. The current creates a magnetic field. The magnetic field will create induction in the rotor. So the rotor, because the part that is rotating, works like a magnet. And as it rotates, it now creates an alternating magnetic field inside, which from the inductors, from the circuit's perspective, appears to be a voltage applied to it externally. That's an induced electromagnetic force, an induced voltage. They're going to call here Vm, that is applied externally to this circuit as a result of the rotation of the rotor that is magnetized by the current in the circuit. You guys know what I'm talking about? Yeah? Okay. So this back EMF that we're going to call it, the back electromotive force, is simply an external voltage applied to the circuit. We can now model this using Kirchhoff's law. And you can say that the input voltage V of t in Laplace V of s equals to the voltage drop across the resistance of the winding in the motor plus the voltage drop across the inductor plus this external voltage that I'm going to call Vm of s. That is the voltage induced by the rotation of the rotor in the state. Right. And you can now solve here for I of s. We can factor out I of s on this side plus Vm of s, and so for I of s, which is Vs minus Vm of s divided by Ls plus R. So once again, V of s is the input voltage, is what we apply to the system. Vm is the back electromagnetic force that comes from the rotation of the rotor, and R and L are the characteristics of the winding itself. Okay. Now that's the electrical part. Now we need to somehow link the electrical and the mechanical part. And the first relation that you can establish there is to make the observation that when a magnet moves, let's put it this way. When you have a changing magnetic field in a conductor, that creates a voltage. The faster you move that magnet, the higher the voltage is. So we can say that this induced voltage is proportional to the speed of the motor, where Km here is simply a constant that depends on how we build the motor. Omega s is the speed. So what you're saying is the faster it turns, the more voltage it induces in the rotor, which is pretty much what Faraday's law states. Right? If you have a conductor in a magnetic field, the relative speed between them will create a voltage, and that voltage is proportional to the speed between the magnetic field and the conductor. Yeah? Any questions? All good? Okay, so we have two equations here to start from. We have the electrical part. We have here a link between the electrical and the mechanical, and they are summarized at the bottom here. Now we can move on to the mechanical part and see what happens on that front. From the mechanical side, the current that is developing now through the armature, through the circuit that we just calculated, creates a magnetic field. That magnetic field induces a current in the rotor, or maybe assuming that the rotor has a magnet in there, there will be an interaction now between the created magnetic field and the rotor. And that interaction creates a torque. Right? So the electrical part, from the mechanical part's standpoint, creates a torque. And you can say here that is going to apply a torque like that. That will now drive the shaft of the motor. And you can later establish a relation between this and the electrical part. But for now, let's assume that all what the electrical part is doing is creating that torque. We can now do the sum of all torques equals to acceleration, angular acceleration times inertia. So sum of torques equals to inertia times angular acceleration, which is the same as omega s times s, the derivative of the speed, right? The derivative of the speed is the angular acceleration. And what are all the torques acting here? Well, first of all, we have the torque that comes from the electrical part. Second of all, we have friction between the shaft and the bearings and everything there. And let's assume that that coefficient of friction is B. So minus B times the speed. And why is that minus? Because friction in this case always opposes motion. Right? So if you are rotating, if T of S is creating a torque clockwise, the friction is going counterclockwise. and minus a external torque that we are driving. So let's assume that this external torque is a load. It's something external being applied to the motor that we are driving. Right? It's not part of the motor. So that's another component there. And this is equal to j omega s times s. We can now factor all terms with omega of s. That's js plus b, which means that the speed now can be written as the net torque. Makes sense, the net torque divided by js plus b. Does that make sense? Yeah, are we okay with all these terms? We know what they represent. Sorry, I can't hear you. Yes, so the TD. Yeah, so TD is an external torque, an external force acting on the system. Let's assume that this is connected to, is a fan, for example, connected to propellers, and the resistance between the air and the rotation, it could be seen as an external torque acting to it, something you have to overcome. Or it could also be if we hang a weight here, is a torque that is being applied to the motor that is trying to accelerate the motor, but we are trying to work on in the other direction torque. Now we have to establish a second relation between the mechanical and electrical part, and that's through the torque applied by the motor. We know that from electromagnetism that the torque will be proportional to the current in the armature in the motor. And we can go into the details of that, but for later. But for now, let's just assume that this assumption holds. Torque is proportional to the current in the motor's armature. Right. Well, the greater the current, the greater the magnetic field, the greater the interaction between the magnet in the rotor and the magnetic field will be, the greater the torque there. So current now influences the torque, while speed influences the back EMF voltage in the armature. So now I have a set of 4 equations to work from. And let's put them together and create a block diagram to represent them. Our objective is to determine the relation between the current and the speed in the output. So we could very well have a transfer function, but if you do a transfer function between voltage and speed, then you don't have access to the back EMF. We don't know what it is. We don't know the current. All that information is lost because you now combine all these transfer functions into one. So let's take these functions here and see if we can represent them using a block diagram and see if that helps. How do we start? Well, these are the equations we just derived. Let's start from the input. Where is the input in the first, second, third, or fourth equation? The first one, right? The input is what we have control over, which is V of S. And you see V of S showing up on top there. So let's start with the first equation here. That's where the input is. Input is what you have control over. So this is V of S. And you can see that on top of the equation, we have V of S minus V. That should have been Vm. This is Vm. So you can now create that subtraction then by simply adding a sum here with a negative sign. This is Vm of S. And what do we do next? Well, we created the top of the equation. On the output, the arrow in the output is Vs minus Vm. And notice now that if we divide that by Ls plus R, what is the result? It's I of S. Let me write it here and let you think about it. If I multiply this by 1 over Ls plus R, the output here is I of S. Do we see that? The result of this operation here is Vs minus Vm, the top of the equation. I'm now dividing the result by Ls plus R, and that gives us I of S, which is equation 1. Does that make sense? Yeah? What do we do next then? Well, we have I of S. Now, if you look at the third equation, here, we see that if you multiply IS by KI, the result is T of S, isn't it? The result is T of S. And what do we do next? Now we can continue our reasoning and go, let's say, to where T of S is, which is equation 2. Now, if you take T of S and subtract TD of S from it, we get the top of the equation. And if you multiply that by 1 over JS plus B, what do we get in the output? Omega of S. It's equation number 3. Same as number 1. Now for the mechanical part. And what do we do now? Now we can go to our last equation, equation number 4. We see here that if you multiply omega by Km, the result is Vm of S. So that can be connected back to the input, to the sum in the input, and that closes the loop. Okay. Now this represents all these 4 equations. Now notice something interesting, that we have access to everything now. If you think about using this in Simulink, we can put scopes and probe the signal anywhere on this diagram instead of just having access to V and omega. We can look at how the current behaves. We can look at how the back EMF force behaves, the speed, and so on. Let's take this one step further and calculate the position. How do you do position from this? How would you use this to calculate the position of the motor? We do the integral of speed, and how we do that in the frequency domain, we simply multiply that by 1 over S. That's now the position of the motor. If you simulate this and look at the current, something interesting happens. You will very likely see something like this. So this is time, and this is the current. And you see a peak, and then it stabilizes later. Why is that happening? Notice that when you turn the motor on, the speed is 0, that a feedback loop is 0. So nothing is subtracted from V of S. The current then is simply 1 over R, and it's going to spike. As the motor starts to speed up, now the back EMF loop, Km, is not 0 anymore. And now we are subtracting a voltage from V of S, and the net voltage applied to the circuit decreases. So does the current. And then eventually it settles. So that is spike that you see when you turn on a motor. You can clearly see that in the wires when you turn it on. That comes from this feedback loop that exists inherently in the workings of a DC motor. And once that the motor starts rotating, then that spike goes away, because now the feedback loop is activated. So when you buy a motor, you have typically the nominal current, which is the current after everything's settled, and you have the stall current or stall torque, that is the maximum current there, which for a small DC motor, if you get one from Maxon, they are like 40 millimeters in diameter. The stall current is something crazy like 80 amps. And the nominal current is 2-3 amps. And that's because of this feedback loop. So that the system cannot, of course, sustain that for long. Everything is going to, it will simply destroy the armature. But that phenomenon happens, and typically happens for a few milliseconds if the motor is constructed well until it starts to speed up. Any questions? No? Okay, so here is the entire model. I posted a Simulink model in Brightspace. You can download it there and see what I'm talking about in terms of current, speed, and how it behaves. You have two files, a Simulink and a MATLAB file. So the MATLAB file defines the variables. So run that first, then run the Simulink and investigate the effects of these parameters there. So that's posted in Brightspace. We're going to skip that now. Now let's do something a bit more generic. So that was specifically designed for the DC motor, but we can apply the same approach to pretty much any system. But most of all the systems we are describing, we are using and simulating, they are governed by differential equations. So now let's establish a framework to create block diagrams from any differential equation. So here I have equation 1. That's the most generic form of differential equation that I could think of. You see on the, what is this? This is the left side. You see on the left side the derivatives of y, which is the variable of interest, right? That's the output of the system. That's what we are solving for. And you see the other side, that these variables will depend on the input, that's r of t, but also on the derivatives of r of t. Right, so this couldn't be more generic. We can use this for any systems. And once again, the input is r, the output is y. Does everybody see that? The output of the system is what we are solving for, and that's y of t. Now, how do we do a block diagram for this guy here? This is a bit more involving because we now need to get rid of these derivatives and integrate the equation as many times as we need to get rid of all these derivatives. So the first thing to do is to look at the highest derivative. That will always appear, will be associated with the input. And in this case, here is the third derivative of y. So a3y triple dot is the highest derivative element. We can now, first step is to solve for that. So if you isolate for y triple dot, we can move all other elements to the right side of the equation. And you notice here that I'm grouping terms with the same degree of derivatives and then putting them together. All right, so these guys go to the other side, they become negative. Here it is, associated with r double dot, y double dot, r dot and y double dot, r and y. I'm just grouping them together for simplicity. And now if we want to solve for y, what do I have to do? Well, it's simple, just integrate it 3 times. We have a third derivative, integrate it 3 times, that will give us y of t. So that's where these integrals come from, right? Triple integral now gives us y of t. We still have the derivatives inside and we don't want them. We don't want integration and derivation. We can use these integrals to get rid of those derivatives, and I'll just have y of t as a combination of integral functions to solve for y. Are we good up to this point? Yeah? Okay. How do we get rid of these derivatives now? You see that the 3 integrals are integrating the entire function. What we can do to get rid of these derivatives is to now take one integral at a time and slide it through the function, and as we slide and pass through the derivatives, we drop the derivative. What I mean is, if you take this integral and then move it to that side, this term will come out of the integral. So we are taking the integral of it, and then this double dot becomes 1 dot. Does that make sense? I'm just sliding the integral over, and in the process, I'm integrating that term. So that integral, if that integral makes it over here, it is no longer integrating 3 terms now, it is integrating 2 terms, which means that these 2 terms that it passed over here have been integrated, and they are now simply r and y dot. Yeah? And I can do the same for the other term. If I move it 1 step over, Now I'm moving it all the way past there and here, so it's going to come all the way there. Now this becomes dot, this is dot, and this is simply not dot and just not dot, and the integral, the last one, remains. We still have one integral, two integrals so far, and one derivative. So the derivative in the middle there, we can now take the other integration and move it over there. And we move it over there. These two derivatives are integrated, they disappear, and now the integral moves to the second position. We can no longer slide it on because now we got rid of all derivatives, right? There's nothing else to integrate. You have to stop there. So if you bring in the integrals to remove the derivatives, we get the equation in the center there. Does that one make sense based on what we discussed? Yeah, and these variables that you see appearing here, tau, zeta, and lambda, they are just dummy integrals that will disappear once the integral takes place and everything goes back to time. Now you see that time is the variable of integration in the last integral, so everything eventually goes back to a function of time. Does that make sense? Are you sure? Yeah. All right. So what I'm doing here is basically just sliding these integrals over to the right, and as I pass over derivatives, I just take the derivative out. I'm just integrating the functions. Now notice that the resulting equation is in integral form. All the derivatives are gone, and we have an integral form only. That's the same equation we got. Now let's try to create a simulation diagram for this. Where do we start? Where do we start? We can start with the input, the system, which is R. And you notice here, let's look at this term. This term, how many times has this term been integrated? Three times, right? The middle one has to be integrated one time, and the most left one time. Two times in the middle and one time to the most left one. So let's start with the one that requires the highest number of integration. Be 0. We can subtract a0 y of t. We'll find that somewhere later. And the result now needs to be integrated. There. I could, if we are dealing with frequency domain, then the integral becomes 1 over s, of course, and then all t's become s, right? It's the same representation. Just that my main function is in the time domain. So I'm going to stick with that. So that takes care of the first term. So that has been integrated already once. Now we can add to that the second term here. Second term takes r times b1. So I have b1 here. I can probe r there and move it here. Right? The output is r times b1. And I want to subtract a1, excuse me, y of t, which is that. And now we can take the integral again. And the result of this blue part, the purple part, is the center integration. Right. And now we have the last one there, and the last one is it requires plus b2 times r. So we can go pick off r over there. We are subtracting what a2 times y of t. The result of this now needs to be integrated once again. And at this point, what have we created? We have all these integrals together. Don't forget the 1 over a3. Now I have to multiply the entire thing by 1 over a3. And what is the result? What is the result? Y of t. Very good. Y of t. This is y of t. And now we have y of t. We can connect the missing information here. This one is a2 times y of t. So just move a2 here. There we go. That one is a1. And the last one is a0 times y of t. And that's the simulation, the simulation diagram for that transfer function. Now, we mentioned in the beginning that the red one, the third one to the what is this? The right needs to be integrated 3 times. Is it indeed being integrated 3 times? It is, right? Look at our signal that the signal we created inside here, the integral. Let's call that a. A would be over here, just before the integral. Notice that for a to make it to the end, to y, it will pass through 3 integrals, right? So it makes sense. Right? It makes sense. Okay, so this might be a bit intimidating at first, but any differential equation can be written like this. So this is generic. Every time you have to do a differential equation, you'll follow into this specific type of diagram. The only difference is these variables b and a, which of course will depend on the system in question and how many integrals we'll need, which corresponds to the degree of the transfer function. Right? So once you do this once, you're good. Everything else will be precisely the same. Now, why are we bothering with this? Well, again, rather than having a transfer function between y and r, we have access to all these internal variables, and we can probe them individually. All right, let's say that the output here was the speed, was a position. Then just before the integral, we have the speed. Just before the other integral, we have acceleration, and so on. Right? So all these internal signals are available there. Yep. It's a lot nicer than using differential equations, isn't it? And Simulink is built exactly for this type of work. And indeed, next labs will be using this, and also the next assignment that I'm hoping to finish today. How was the first one? Was it too long? Was it doable? Too long? Right lane? Nobody's complaining. I'm good with it. Shorter would be better. Yeah. No, it was a bit tough. I will give you that. But the first one is important. There's a lot of fundamental concepts that we need later, so it's good to insist there first. Okay. Any questions here? No? Okay. So if there are no questions, let's do exercises, and hopefully that will make things more clear. Let's start with this one here. This is the one we had in the first slides. The position control system of a spacecraft platform is governed by the following equations. We have a set of 4 equations, and you want to sketch the simulation diagram to represent the system. So let's look at these equations. We have a desired position, which seems to be what we want to control. Right? That's the input to the system, is where we want the position to be. So that's clearly the input. We have the current position, which is the output of the system. If we are controlling the position, this is the output. Right? The desired is the input. Then you have 3 internal variables: the amplifier input voltage, the amplifier output voltage, and the motor shaft position. So what you can guess from this equation is that from desired and the current input will create an error. We will compare them to see how far we are from where we want to be. Then that result will go through amplification stages, V1 and V2. Eventually creates a voltage that is applied to a motor. and the relation between the motor shaft position and the amplifier, the motor shaft position and the position of the spacecraft, then is given by the top equation there. Okay, but for now, we identified everything we need, the input and the output. So let's try to derive the simulation diagram for this. Here are the equations, and let's start where the input is, which in this case shows right there. Remember that that's the desired input. Let's do this in the frequency domain. R of S is right there. We can subtract P of S, and the result is V1 of S. Right, that comes from the first equation there. Now V1 of S is a voltage. Let's see what that means. It's amplifier input voltage. Okay, so the amplifier, the difference between the current and the desired output, current and desired position, creates this voltage, and this voltage is now given to the amplifier. Amplifier is V1 is now shows in the last equation. We can simply multiply that by 8, and this gives V2 of S. Yeah, so now we amplify that voltage, and where does that show now? Now it shows in equation 3. Sorry, this was supposed to be equation 2. And this is now equation 3. So equation 3 says the rotor, the derivative of the rotor of the shaft, how did he call that? The theta is the motor shaft position. So basically, we are controlling the speed. Look at this. We are controlling the speed of the motor based on an input voltage, right? As d theta, dt. So the speed of the motor now depends on this voltage that we're applying to it. So if I multiply V2 by 0.5, what do you get in the output? What is the output there? Is the derivative of the motor shaft position, which is d theta dt, or theta s times s, right, in the frequency domain. Okay. Now theta s times s doesn't show up anywhere else. What can you do to get rid of s? Just integrate it. All right, so we now take the integral here. We have theta s in the other end. Now we had the speed integral, now is the position. Now theta s shows in the first equation. Now the first equation, we need to work that out a bit because we have the output will appear there, and the output seems to be now governed by this differential equation. Now we have no choice but to take the Laplace transform of this and find a transfer function. What is the Laplace transform of that? Is P of s times s squared plus 2P of s times s plus 4P of s equals to theta of s. So I can factor out P of s squared plus 2s plus 4 equals to theta of s. And now P of s is theta of s divided by s plus 4. Now, what is this equation giving us? This seems like a transfer function that relates the position of the motor to the position of the spacecraft. And what is that? S squared plus 2s plus 4. That's the dynamics of the spacecraft. We are changing its position. The bottom there, these s's are probably coming from, well, they come from this differential equation. They represent the dynamics of the spacecraft. What do we do next? Exactly. So do the transfer function first, and then the feedback loop. Yeah. So if we have theta of s there, if we divide theta of s by s squared plus 2s plus 4. The result is P of s. And now we can close the loop. All right, so look, this makes much more sense than the equations themselves. Right? When you look at the equations, it's hard to tell where we are going. I was giving you that a little explanation in the beginning because I knew what the result of this manipulation. But if you look at the equations and you look at the block diagram is a lot easier to understand. We see how everything is connected, how all these four components work together to change the position of the spacecraft. Right, so the first two gains there, 8 and 0.5, are amplifiers. The amplifier changes the speed of the motor. We integrated that to get position. And now we have a transfer function between position of the motor and position of the spacecraft, which captures the dynamics of the spacecraft. Good? Any questions? No? All good? Yeah? Okay. Let's do another one then. Yep. Yes, you could certainly do that, but you're kind of throwing away information, right? Because now V2, if you do that, V2 is gone. And what if, for example, that amplifier only accepts can output a maximum voltage of 24 volts? You won't be able to know, right? You only have V1 and theta, but you could certainly multiply everything. And if we can actually multiply all of them, all four, and just have the feedback loop and then eliminate the feedback loop, that will give us a transfer function. We'll see that in the next lecture. Good? Okay, let's do, this one is very similar. Let's see which one. Okay, let me see your time. Okay, let's do this one. We need this for the assignment. And then we'll do another one if you have time, where you do the differential equation. So here we have a robotic system that operates on patient. And these equations represent the position and orientation of an ultrasound probe, and the position of orientation of a surgical arm. So basically, it seems like we have two robot arms. One is controlling a surgical tool, and one is controlling the position of an ultrasound probe, and they are operating on a patient. F of t and g of t are the desired positions for the surgical tool and for the ultrasound probe. Everything else basically is the dynamics of those robot arms. And you notice here that there is the position of one robot arm is x, the other one is y. But we see that in this differential equation, we have y, and in the other differential equation, we have x. So basically, the position of one robot arm is affecting the position of the other one. They are somehow interconnected. And we want to create a single block diagram to represent differential equations in the frequency domain. The block diagram cannot contain any elements with transfer functions. Only use sums, gains, and integrators. Oh, this is going to be fun. Yeah. Okay, so two differential equations. First differential equation, desired position of a robot arm of the surgical tool. That is a function of all those states and all those derivatives, but also a function of the position of the other robot arm that is governed by the second equation, which itself is a function of the first. So this is a typical problem in robotics. If you guys are interested in robotics, especially specifically in surgical robotics or mechatronic systems for medicine, that's what I do for my research, and it's taken from there. So if you're interested in research in the field, let me know. I always have positions for students. summer positions or even part-time positions in the field. And you can stop by, take a look at the lab, see what we do there if you're interested. All right, so let's do it. So here we have the two equations. And it's a lot easier to get rid of these derivatives first and do the Laplace transform. So here I have the Laplace transform of them taken in the second row. Right, nothing new here. We see the fourth derivative becomes s to the power 4 and so on. Nothing new there. And then in the third part there, what I did is I rearranged these equations based on the highest derivative. Same thing we did before. Right, the equations are rearranged to solve for the highest derivative. What does that mean? Well, and why did I do that? If we are able to now create expressions or block diagrams for the right side of both equations, we'll have the variable of interest, the fourth derivative of the variable of interest, which you can then integrate 4 times simply to get to the output. That's why I'm highlighting it there. And same goes for the second equation. I'm just rearranging the equation and solving for the highest derivative, which in this case is y triple dot or s to the power of 3 times y of s. Any questions here? Now, how we got to these equations? Is it clear? So the first manipulation is just the Laplace transform. The second manipulation is the just solving for the highest derivative. So this is our starting point. Are we good? Make sense? Okay. Very well. So now these are the two equations we have to work with. Let's start from the input. Let's take the first equation to begin. And the first equation, there has an input f of s, and the output of that equation is x of s. So let's write the equation here. Let me use a color, it's easier to see. This is f of s. And from f of s, we can now subtract this term, which is c times x of s times s. We can subtract that term, which is b times x of s times s squared, or second derivative of x times b. B is a constant. We can also subtract, what is that? Ax of s, s to the power of 3. And also take this from the top because that's y, that's d times y of s. What is the result of this manipulation? Exactly, x of s times s to the power of 4. Basically, all the sums, they are giving us the right side of the equation, which equates to the left side now, and that's the fourth derivative of x. What do we do now? We can start to integrate. And how do we integrate? Well, just multiply things by 1 over s. The result here is x of s times s to the power of 3. Third derivative, integrate once again. X of s, s squared. Integrate one more time. X of s times s, and a last time to get to x of s. And then you may ask, well, why didn't you just do 1 over s to the power of 4? Because we need their derivatives to complete the loop, right? You notice, for example, that in this loop here, we need as of s times s to the power of 3, which can be taken from there. Just take that signal, multiply by a, and input it there. Now we also need bx of s, s squared, and here it is. Just multiply that by coefficient b and feed it back there. And finally, c times x of s times s. There we go. And you need also d, but d is not ready yet. Sorry, dy of s, that's not ready yet. That comes from the other equation. Does that make sense? Yeah. Now, if you think about, let's say, for example, one of those circuits that we had where you had two loops, two currents. We have two equations, and the equations, the first equation, we have the current in that loop and the equation in the other loop. And the other loop, we have the equation in the other loop and the equation in the first loop. So they are also interconnected. And this is kind of similar to this, because now we have to move on to the next equation. The next equation depends on the first one. The input to the second equation is g of s. And we have to subtract b y of s squared. And you also want to subtract d times x of s. And what is the result? A y of s times s to the power of 3. Now the first one, we had x of s times 1 times s to the power of 4. Now this one is multiplied by a. So to get rid of that a, multiply by 1 over a first. So now you have y of s to the power of 3. The first one, we didn't have that. The coefficient that multiplies the term there was 1. And now we can start to integrate one time y of s squared. Integrate one more time s, and integrate one more time to find y of s. Now we need b y of s squared. Here is y of s squared. Multiply that by b. There we go. And finally, we need to connect d, this input here, d x of s. So x of s will come from the other equation. We can take it here, multiply that by d, and this is where it starts to get messy. And there it is. And same goes for y. Y needs to be multiplied from this top loop here, the top input. We need y to be multiplied by d again, and then be fed there. And that completes the loop. And so this is a very good example of two equations that are interconnected. And this will appear in most systems. In a mass spring system connected with a spring, the displacement of one mass is influenced by the displacement of the other one. So we will fall in this category as well. Now, we mentioned in the beginning that x of s is the position of each arm. So if you want to know the position, just probe the signal right here. If that is position, what is this signal? Well, this is the speed. This is the acceleration. And that's jerk. Right, just before you integrate the signals. Now notice also that there is no derivatives here. If you end up with a derivative in your calculation when you create a block diagram, something went wrong. We can never have a derivative by itself because a transfer function, remember, it always has the degree in the denominator higher than that of the numerator or equal, but not the other way around. All right, so physical systems will never have more derivatives than integrations when you do the transfer function. Well, that's not entirely correct. It should say in the transfer function, the degree of the degree on the left side of the equation, the right side of the equation is always greater. The degree of let me put it this way properly. The degree of the derivative of the output is always the same or greater as that of the input. Right? Never the other way around, meaning that the denominator of the transfer function always has the same degree of the numerator or a higher degree than the numerator. Does this one make sense? Yeah. Times it. Okay, shall we move on to another one? Yeah. Maybe let's do this one. Derive a simulation diagram for the following differential equation. What do we do first? How do we start? So solve for the highest derivative of the output. The output is y. So we are solving for the highest derivative of y. That's y triple dot, which is 5 times times what? Times 6r double dot minus 4y double dot plus 2r dot minus 3y dot plus r of t. I'm just grouping the terms with the same degree of derivatives together. Yeah? Does that make sense? And what do we do next? Oh, now you have to integrate this 3 times if you want to find y of t. I'll take the liberty here to call everybody t, just for simplicity. But it's not t. There's a mathematical crime there, but that's fine. Okay, let me do this properly. It bothers me a bit. So dr d alpha dt. Now what do we do? Now we can start to move these integrations over to get rid of the derivative. So let's start by sliding this integral all the way to r of t. And as we do that, we are passing over the first 2 terms. They are being integrated once. So we now have 6r dot minus 4y dot plus 2r minus 3y plus integral of r of t dr d alpha dt. So a reminder that the first 2 integrations there are integrating the whole thing, right? Not only the first term. They are integrating integrating the whole equation. Does that make sense? Yeah? No? What do we do next then? Well, now it can take another integral and move that over as well. We have to this time stop at the middle there, because past the first term, everything else, all derivatives are gone. So we can slide this integral here, and in doing so, we'll have 5 integral of 6r minus 4y plus integral of 2r minus 3y plus integral of r of t dr d alpha dt. Now remember that this integral is integrating all terms up to this point, and this integral is integrating everybody as well up to this point. Actually, there. Yeah. Yes. Yes, so the first integral integrates all three terms, the second integral, the second and the third term, and the last integral, only the third. Because the third integral already integrated the other two. Is the brightness better or it's still too bright? Good. Very well. Can we move on? Now all we did was to prepare this beautiful equation. Now let's create a diagram for this. Where do we start? We always start from the input. The input is R. Now which of these elements should we start from? The most right one, right? Because that one needs to be integrated 3 times. So if you move it to the beginning, as it goes through the system, it will be integrated 3 times. So let's give it a name. Let's call this R of t. We could do R of s. Let's do R of t. And this is already integrated right away. We are integrating this. And now we are adding to this signal 2 times. This is a terrible drawing. 2 times R. And now here, 2 times R. And minus three times y. And I'm taking the integral of that. This integral is that integral. Does that make sense? Yeah. So now this term is basically here. And this term is over there. Now we have the last term. We have to add 6R. So we can take R from here and multiply that by 6. And you are subtracting 4y. The result is integrated. And what is the output there? Well, the output is now the output of all these 3 integrals. We have to multiply that by 5 now to get y of t. So this multiplied by 5 is y of t. And now we can complete the loop. We have y of t. We need 3y and 4y. Well, just probe the signal there. Multiply it by 4. Here we go. Same thing. Multiply it by 3. And here we are. And that's the complete diagram. Now notice again that the signal R of t, for R of t to get all the way to the end, it will have to be integrated 3 times. It has to go through the line, and as it passes through, it is indeed integrated 3 times. So that gives you an indication as to whether the simulation diagram makes sense or not. It agrees with the transfer function. And notice that this is exactly the example we did before. It's just smaller in size, right? And the only thing that changes really is how many integrals you have, how many loops you have on top and the bottom, and their coefficients. But it's always following the same sort of simulation. Okay. The difference compared to this one that we did before is now these feedback loops. Notice that they are being probed at a different points, not all at the end, right? Unlike the ones we just did. But these are the 2 forms that you'll find most of the time. Okay. So in the assignment that is coming out today or tomorrow morning latest, this is the sort of diagram that I will be looking for.